Okay, so we will continue now. So real poles, complex poles, real poles of multiple order, or complex poles of multiple order, that is. We will continue here. And your corresponding function of t is processed using the partial fractions, in which the constants you have determined. In your calculus, what you do with this expression is you integrate. In the case of Laplace transformation, what you do is differentiate, is rather inverse Laplace transformation. You integrate. When you do it in integral calculus, in here you invert individually the terms here and convert them to the function of t. Okay, now you could see this expression here. I like to use the board for this one. That way you will understand how this is to be done. Okay, so I'd like to go to the board and see. Stop sharing here. And we'll go to our share a new screen, and I will use the board. That way it's clearer. Okay, do you see the Jamboard, class?
Yes, Miss.
Okay, so I will just, for now, it's s plus 6 over s squared plus 3s plus 2. So I'd like to go back to the board. Just inform me if you cannot see. So in that particular function, your given function of s in that case is s plus 3 over s squared plus 6s plus, I think it's a 13. Wait. S plus 6, 3s plus 2. So this one, s plus 3, this one is 6s plus 2. Now, if you notice, this is not factorable. It will yield the, by the way, it's, if it's a 2, is it 6s? Wait, class, let's check. 6 and 3s. 6 and 3s. Insuli ko naman siya, class. Wait lang. This is 6 and this is 3s. Okay, we will start with something that is factorable. So this one is factorable. Okay, so what you do, you rewrite it as s plus 6 over s plus 2 s plus 1. So I will just review you in the method of partial fractions in the case of these real roots. So the rest I will leave to you, because anyway, you know your method of partial fractions, I'm sure, in your integral calculus. So you have s plus 2 and s plus 1. So you will have here an a for s plus 2 factor. We call this, by the way, the partial fractions, the method of partial fraction, and you will have the b over the s plus 1. If you will have this expanded, you will have this expanded quadratic equation. So now you have learned, in whatever form Miss Niti have taught you, that this should be s plus 6. And you have here a times s plus 1 plus b over s plus 2. I'm sure since you're dealing only with real roots, you just need to assign a value for the s in which one of your coefficients will be set to 0, or one of your terms will be set to 0. So if you set it as -1, this would be 5. The left side would be 5. This will be 0, and in here you will have b, because this is negative 1 plus 2, that would be 1. So, sorry, it will now be b being equal to 5. If you set s, this time we set this one to 0 equal to negative 2. So if this is negative 2, the left side would be a 4. And this one would be 0. If this is negative 2, this would be negative 1. Negative 2 plus 1 is negative 1. So then A must be negative 4. Now, having the values of A and B here, you're now ready to invert. So your function of S is now inverted. This is how we write the inverse Laplace. We use the bracket. It's S plus 6 over S squared plus 3S plus 2. Now, the inversion will be carried out per term based on the partial fractions that you have here. Your A has a denominator of S plus 2 and has a coefficient of negative 4. So the way you write it is negative 4 inverse Laplace. That's for your A, 1 over S plus 2. Now, you may wonder why, Miss, why did you not write the negative 4 in here? It's because we know that if we are to invert a function of S in which the denominator is a constant, the constant in the numerator should be a 1. So my 4 should be written here. Okay? As for my B, your B has a value of 5. And the denominator is S plus 1. So this should be 5 inverse Laplace of 1 over S plus 1. If you have this inverted, you will have negative 4. The inverse Laplace of this is e raised to negative 2t. And that one, the second term is 5. That's not s. E raised to negative t. And by the way, your function of s when inverted will not yield the function of s, of course, but it is now yielding the function of t. So your function of t is the inverse Laplace of the original function of s. Now, if you would like to get the Laplace, this is how I write it when I say it's italicized, and you will use the braces this time, not the bracket. If you need to transform this, your answer that is, the answer should go back to this when simplified. So if your answer here goes back to the original function of s, then you're doing the right thing. But the thing is, what you did was use the method of partial fraction because your denominator is factorable. Even if it's not factorable, you can still use the method of partial fraction. Another thing that you can do here is you can also use completing the square class. So what you're going to do is this. It's s squared plus 3s plus 2. I will illustrate another method. So you will have the inverse Laplace. By the way, the exponent is negative 1. So I will have here s squared plus 3s. Now, what particular constant will you add to 3s and s squared to make it a perfect square? So this should be divided by 2. That should be 1.5 squared. 1.5 squared is, anyone who has a calculator, let me see. Your 1.5 times a 1.5 will yield a 2.25. So this is another method that you can use, 2.25. Actually, it's not on the standard formula that I have shown, but you will see. Your original denominator class is 2, right? So what do? You add 2. You add 2 here that you need to subtract 2.25. Why do you need to subtract 2.25? It's because this 2.25 was added to make this a perfect square, and you want it original. The original only consists of this, the s squared, the 3s, and the 2. So then what you added here, you subtracted here. Okay? Now, this is an alternative way of doing it. Now, your numerator, on the other hand, I'll go back to the numerator, is s plus 6. So, before you alter the numerator, make sure you write your denominator in the perfect square form. So, this is like that. S squared plus 3s plus 2.25 is actually s plus 1.5. Miss, where did you get the 1.5? That came from the square root of this. Okay? And you will have a 2 minus a 2.25 is a negative 0.25. So this is negative, and the 0.25 when square root, when you take the square root, would be, I think, your 0.5. Your 0.5 squared, when you square it, that would be your 0.25. So this is now 0.5 squared. Okay, your numerator, which is s plus 6, you have no choice. You really have to convert the s to s plus 1.5. What do you lack to make this one a 6? Simple. You have to add here. You have to add just like what you have done here. You have to add 6 minus 1.5. Now, what happens is, the 1.5 here and the 1.5 here cancels each other, giving you a s plus 6, the original numerator. But the thing is, you have already done the completing the square here. So this is just for those who would like to go to completing the square. But if you don't like this process, it's fine. So you have here now an s plus 1.5. It's better that you see me do this so that you will know how to do it yourself. So s plus 1.5 squared minus 0.5 squared. Okay? That's your one fraction. This one will be separated. Now your 6 minus 4.5 is actually 4.5. Right? It's 4.5. 4.5 plus 1.5 is 6. So what you do is you place here 4.5 inverse Laplace of, I'm showing to you the trick. So you have same denominator here. So s plus 1.5, it's difficult to write. Squared, ay putang ko lang dito lang. So 0.5 squared. Kaya mo ng denominator mo. Ang baba mo if this is your numerator rather, where am I? Your numerator here, if it should be a constant, should be 0.5. So what I do, I put here 0.5. 0.5. What you do in calculus, if you introduce a constant, you divide by a constant. Right? So now you will have an answer. So this one, your function of t is equal to this one. You account for it, the e raised to minus 1.5 t. Now, for this first fraction, this is, take notice class, that it's now minus. Minus. It's not written in the standard formula of the transforms that I have given you. So I'd like to go back to that first. I'd like to borrow maybe 2 minutes of your time. Wait. I'll share a new screen. New share. Where is it? Okay. Okay, I'd like to go back to my table. You see this formula, class? Sine and cosine, positive and negative. If you change the positive here into minus, same thing here, if you change this to minus, instead of the sine and the cosine here, same thing here, it will now become hyperbolic sine, hyperbolic cosine. Hyperbolic sine, hyperbolic cosine. So this, if this is negative, if this is negative, same thing with this negative, the original sine and cosine functions you have will become hyperbolic sine and cosine functions. Okay, take note of that. So I will now stop sharing here and go back to my board. So you just have to share again this one. So this is now, I already factored out the exponential part. So this is, since it's sine, this would be, since this is S rather class, this is hyperbolic cosine of 0.5t. This one, you divide your 4.5 by 0.5, so that would be a 9. And this one, since this is a constant, this is an S, so this constant must be hyperbolic sine of 0.5t. Hi. This is another solution to this one, to this which you processed using method of partial fractions. Now you may say, it's totally different than your answer, Miss. This one is totally different than the one that you gave us, the simpler one. Now, if you recall in your integral calculus that the hyperbolic function and specifically the sine and the cosine of hyperbolic function, it's equivalent to exponential function. In the case of hyperbolic cosine, this is e raised to 0.5t minus e raised to 0.5t hyperbolic cosine, wait, it's e raised to 0.5t plus e raised to minus 0.5t over 2. If it's hyperbolic sign, the only difference is a minus. So this one is e raised to 0.5t minus e raised to negative 0.5t over 2. This one is e raised to 0.5t plus e raised to minus 0.5t. If you will expand this, in that particular equivalent expression, you will go back to the answer that you were given here. It will be equivalent to this. But the reason why I've shown this to you is so that you will know later on that your basic functions actually is not only limited to the sine and the cosine, but at some point in controls, you will see the hyperbolic cosine and the hyperbolic sine. Okay? Now, I'll go back to my slide because I've already used up 1 minute of your time. I'll go back to the slide, share again. The next part of this discussion actually should be, borrow ko 2 minutes of your time, is the actual meat of Laplace transformation, because now you will determine Laplace transforms of derivatives. So where is it? So far, I have discussed this. This is the one that we just discussed. The solution is in here, but I have presented it to you so you will know how to do it on your own. And we have sample number 7 here, wherein you have already 2 linear factors and you have a quadratic factor. Still using the method of partial fractions, you will have this 25 and 10 and negative 15 and negative 25 for this particular coefficients here. When you'll have this inverted, you will use completing the squares, and your corresponding answer will be the shifted sine and cosine. You were taught how to do this in integral calculus, wherein you don't only have one linear factor, but you have a combination of linear factors, of repeated factors, and even of complex factors, just like this. So amo ni siya class. But the thing is, if it had been with enough time, you can also, I would have also, or actually this is shared to you already, the repeated roots. They are linear roots, but one is already raised to 2. Or this could even be raised to 3. So if this is s plus 2 raised to 3, you will have 3 equivalent partial fractions here. One denominator is s plus 2. The other one is s plus 2 quantity squared. The other one is s plus 2 quantity cubed, depending on how many times this linear factor was repeated. So you have this example here. You can do that on your spare time. Do it on your own. That way you will know. But as to the part of having to use Laplace transform and inverse Laplace transform in determining solutions of linear differential equations, higher order that is, with constant coefficients, this part we haven't yet discussed. So on Friday, since it is your swoot day, I will not have this discussed to you, but rather I will only give a quiz on the portion that I have discussed. So I will stop sharing here. I will stop recording rather.